Math 3 Lesson Summary Video. Eat them to beat them. This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to model with exponentials and find the relationship between growth rates for different time periods. In 2000, there were 3 sightings of lionfish in North Carolina. The number of sightings approximately tripled every year. Make a table, graphs, and write an equation for the number of sightings T years after 2000. So first we want to try and make all of our multiple representations. I'm going to start with a table. So if the first year, year 0, there were 3 sightings, and then it says it triples every year after that. So after 1 year, it's going to be 9, and then 27, 81, 243, 729. So I have a table of tripling every year. So after 5 years, 729 is what I would expect. If I graph that, I've got some points that look like this. So that gives me my data points. And if I think about that as an equation, we started with 3, so that's our initial value. And we're tripling, so we're multiplying by 3 every year. So there's our time, although x would be t. They wanted it in t for t years. So 3 times 3 to the x power. And then I can go in and just graph that line if I wanted to and see if it hits my points the way I expected it to, and it does. So I've got a couple of graphs that I made, the one with just my points and then the one based on my equation. Helps me double check myself and make sure that I've got a good model for this situation. So this is now a model that would predict how many lionfish sightings would we expect in North Carolina after so many years after the year 2000. When will the number of sightings reach 1 million? So we've been doing for the last few lessons, how can we figure these kind of things out? So we know we have our model of 3 times 3 to the t for our years, and we're interested in when is this actually going to reach 1 million. So I can solve by graphing, I can solve algebraically, either one that you want to. If I graph, just remember we have our table and we can graph this line, and then we can go in and graph the horizontal line million and see where they intersect one another. We can also solve algebraically if we just divide by 3, and then that isolates it. And then if I do log base 3 of 3 to the t is equal to log base 3 of 1 million over 3, we will actually find that the number of years before we would expect to have 1 million sightings is approximately 11.6 years. So if that's the years since 2000, we would expect sometime in the year 2011 to actually have 1 million sightings. So what is the annual growth rate? So remember, when we talk about growth rate in our lovely little exponential model, CA to the X, remember A is always equal to 1 plus or minus. If it's growth, it's plus. That growth rate, that percentage. So if our number inside our exponential here is 3, that would, if we're fitting this model, be 1 plus 2. That's how we would get that 3 that's in that spot right there. So that means that our growth rate is actually 200%. And then what is the monthly growth factor? Well, I'm going to have to think about that one for a second. I know that it's tripling in size in 1 year. So that means if I started with 3, 1 plus whatever the monthly growth rate is, and then I know 1 year is 12 months. So after 12 months, I should end up with 9 lionfish sightings because we were told that it triples every year. So if I started with 3, and then I had some monthly growth rate, that's what this is, and then we want it to end up tripling. So we can divide by 3 and say, okay, 3 is equal to 1 plus whatever that growth rate is to the 12th power. And if you remember, if we want to get rid of a power, we are either going to have to take its root, or you could do a fraction exponent and take it to the 1/12th power, its reciprocal power. So I can take that to the 1/12th power. And when I do that, I get that n is approximately 0.0959. Now remember, as a percent, we'd have to move our decimal place over a couple of places, and we get 9.59%. So on an annual rate, over a year, it grows at 200% per year. But if I'm looking at it by month, each month it's growing 9.59%. Now, write a model for the number of lionfish sightings after T years using the monthly growth factor. Okay, so if I still want T to be years, but I want my growth factor to be in months. So I know it's 1 plus my growth factor. So that gives me this. I know I started with 3 lionfish sightings. And I know I want T to be years, but this is the monthly growth factor. So that means I need to do this multiplication every month. So if T is years, I need to remember that there are 12 months in every year. So for 1 year, I would actually have to multiply this 12 times. And so for half of a year, half times 12 would be 6, so I would multiply this 6 times. So I do need to take into account, if T is still years, but this is a monthly growth rate, I'm going to have to multiply this exponent by something to make sure that it actually multiplies the same amount of times. Explain why the equations in part A and part E are equivalent. So our equation that we managed to come up with in part A was y equals 3 times 3 to the x power. And then for our monthly, we have y equals 3 times 1.0959 to the 12x. And we want to show why they're equivalent. There's lots of ways you can do that. You can do that with some kind of paragraph proof and just explain using words. There is such thing as an algebraic proof, where you show work to show that two things are, in fact, equal to one another. So I might try that one. If you recall your laws of exponents, anytime you have a power to a power, then you multiply the exponents times each other. So if I have an exponent that is two things multiplied times each other, another way to write that is as a power to a power. So I could rewrite this as 1.0959 to the 12th power, all being taken to the x power. 3 was still out here, didn't do anything to it, and y was still out here. So this is still the same thing. They're still equal, because if you take a power to a power, you just multiply the exponents. The upside to doing that is that this is just a number, 1.0959 to the 12th power. I can actually type that into my calculator, and 1.0959 to the 12th power actually turns out to be 3.000, then some decimals, but when I round that, I do actually end up with 3. So 1.0959 to the 12th power is equal to 3, which means that these two are actually equal to the same thing.